Imagine being able to download anything you want and print it, not with paper and ink, but by building it atom by atom. Picture a cup that cleans the water you pour into it, a circuit that wastes zero energy, or a hot meal that assembles itself from nutrients instead of ingredients. It sounds like science fiction, but atomic-scale 3D printing is turning that dream into a real-world challenge, and the closer we look, the more exciting and game-changing it gets. If you've ever watched Star Trek, you know the Replicator, a machine that can create almost anything out of thin air. Just speak a command and like magic, it appears. Today we're going to explore how close we are to that vision, what's happening right now, what's still really hard, and how we might reach a version of this that could transform manufacturing, medicine, and energy faster than almost anything else on the horizon. Curious where this leads? Subscribe, like, and turn on notifications to stay ahead of the curve. Let's start at the smallest building block, the atom. Atoms are too tiny to see with regular light, but scientists have tools that can touch and move them. One of these tools is the scanning tunneling microscope, which has a tip so sharp it ends in a single atom. By bringing the tip close and adding a tiny electric charge, it can feel and move individual atoms to create patterns, even writing letters made of single atoms. It's slow and not ready for mass production, but it proves something huge. We can control matter at the tiniest scale. This is the foundational proof of concept, like inventing the first quill pen before the printing press. And it opens the door to reimagining how we build everything. Imagine being able to physically write the architecture of reality. Once you can control atoms, you can start to arrange them with purpose. For example, hydrogen depassivation lithography works by removing individual hydrogen atoms from a silicon surface, making precise patterns that can be used to build the first layer of a device with perfect accuracy. Researchers use this for things like quantum dots and qubits, where the exact position of atoms can mean the difference between a device working or failing. Think of it as programming reality itself. Except instead of code on a screen, it's the physical blueprint of the world, with every line of code representing a physical position in space. But precision isn't just about moving atoms. It's about making sure they stay put in the right spot over a large area. That's where atomic layer deposition comes in. This process builds thin films one layer at a time, using chemical pulses that only react where they're supposed to. It's not quite printing in the way you might picture, but it's like growing matter with pixel-level control, and it already works at the scale of computer chips. Without it, the most advanced electronics in your phone, laptop, or car wouldn't exist. It's the quiet hero behind the gadgets we rely on every day, and scaling its precision into more complex shapes could be a huge leap forward. For 3D shapes, one of the most impressive nanoscale printing methods is two-photon polymerization. It uses a laser to solidify material only at the exact point where two light particles hit at once, creating solid pixels smaller than the wavelength of light. By stacking these pixels, scientists can build tiny lattices, microneedles, lenses, and gears, all at a scale smaller than bacteria. Imagine gears so small they could operate inside your bloodstream, delivering medicine exactly where it's needed, or microscopic tools capable of repairing tissues cell by cell. Electron and ion beams add another trick. They can draw nanowires or carve out shapes directly into materials, acting like nanoscale sculptors that can both cut and build. Then there's DNA origami, yes, DNA, which folds itself into shapes that can hold other molecules in precise positions. This lets scientists assemble materials in solution, almost like giving instructions to nature itself. The potential here is staggering. It's like having millions of tiny builders working in parallel, each one following perfect instructions to create structures that would be impossible with traditional methods. The scale and complexity possible here could rival nature's own designs. So could we build a real Star Trek-style replicator? Not quite, at least not yet. The show's replicator needs two miracles. It has to store a perfect atomic blueprint of any object, and it has to gather all the right atoms and arrange them instantly. That's a massive challenge, requiring enormous amounts of clean energy and flawless control over billions upon billions of atoms. Still, science is chipping away at the problem in creative ways, moving us closer through incremental advances that may one day click together into something revolutionary. A more realistic first step is to limit what we try to make. Instead of anything, we could focus on a set of versatile materials: metals, ceramics, high-tech plastics, advanced 2D materials, and bio-based matter, and combine them into thousands of different products. Different tools would handle different jobs. Some would quickly create the overall shape, others would perfect the atomic details where it matters most. It's a collaborative orchestra of machines, each with a specific role, producing results no single device could achieve alone. Speed is one of the biggest hurdles. Moving atoms individually is painfully slow. The solution? Parallel work. Lasers can already be split into thousands of beams to print many points at once. Arrays of microscopic mechanical tips can operate together. Large-scale systems can roll out films while patterning them at high speed. This hybrid approach, combining fast large-scale processes with precise atomic finishing, may be our best early route to a working replicator factory. The materials themselves also have to be pure and ready to use. Just like a chef needs clean, fresh ingredients, these systems require high-quality feedstocks: gases, liquids, powders, or biological media. Smart factories will treat these inputs like nutrients in a living organism, routing them where they're needed, recycling waste, and adjusting on the fly. This means advanced sensors, AI-driven quality control, and closed-loop recycling systems will be essential. Now think about what this could do for medicine. Painless microneedles for drug delivery, surfaces that naturally kill bacteria without chemicals, and personalized medicines made on site within hours of diagnosis. Picture remote clinics printing life-saving treatments in real time, or surgeries where tools and implants are printed for the patient lying on the table. In energy, it could mean better batteries, more efficient solar panels, and catalysts for producing clean fuels. In computing, it could unlock perfect quantum chips and brain-inspired processors that store and retrieve information at the atomic level. Even consumer products could change dramatically, from water filters that clean as you drink, to plant-based proteins that cook like steak without the environmental impact. Imagine ordering clothes that fit perfectly and feel exactly how you want, made locally with zero shipping waste. This isn't just personalization in style, it's personalization in function, durability, and sustainability. Challenges remain. Atoms naturally shift, contamination is always a threat, and scaling production is tough. Energy must be abundant and clean to avoid trading one problem for another, and anything that can make almost anything must be kept secure to prevent misuse. That means strong regulations, ethical guardrails, and intelligent fail-safes built into every system. The future probably won't give us one magic box that can make anything instantly. Instead, it will be a layered system of specialized tools working together, each excelling at a specific step, creating products that feel like magic. It might look more like a high-tech workshop than a shiny Star Trek console, but the social impact could be just as dramatic. Imagine disaster relief where supplies aren't shipped in from far away, but printed on-site from a library of safe, verified designs. Imagine classrooms printing scientific tools for experiments the same day students dream them up. Imagine neighborhood repair shops making exact replacement parts on demand, extending the life of machines for decades. Multiply those benefits across every community, and the ripple effect becomes staggering. The timeline will differ by industry. Optics and microfluidics are already reaping the benefits. Biotech is moving quickly behind them. Consumer goods will take longer, but computing and energy sectors will push this forward the fastest. Once these domains mature, the momentum could push atomic-scale manufacturing into everyday life, reshaping trade, manufacturing, and innovation itself. We're closer to the Star Trek dream than ever before, but physics still writes the rulebook. We can't create a steak from pure energy, but we can engineer one that cooks, tastes, and behaves like the real thing. We can't build a warp core overnight, but we can bend light with exotic materials. And while that may not sound as flashy, it's arguably even more remarkable because it's happening right now. So when you hear atomic-scale 3D printing, think of it as science and storytelling converging. Science asks, how do we make it real, safe, and scalable? Storytelling asks, how will it transform the way we live? Together they point toward a future where ideas turn into objects locally, with almost no waste. A world where creativity meets precision and imagination literally takes shape. We may not get the perfect replicator anytime soon, but we can build something just as revolutionary. Systems that create at the atomic level, verify in real time, and recycle cleanly when we're done. That's a future worth building. A future where technology becomes a partner in shaping the world we imagine. For more future tech decoded and grounded in real science, subscribe, like, and turn on notifications. This is Tech Mythos.